Today we'll be having a look at dipole-dipole bonding. This is the first in a series of lessons about the intermolecular forces in general. We'll also be having a look at hydrogen bonding, dispersion forces, ion-dipole forces, as well as things like covalent networks and metallic bonding. Before we get started, I just wanted to help us get into dipole-dipole bonding. Let's have a quick look at the word intermolecular forces. We can see the word inter. Just like international travel is between countries, like from Australia to New Zealand, intermolecular forces are forces that exist between different molecules. So I'm going to first give you a quick rundown of to get you an understanding of a dipole-dipole bonding, and then we'll go into some detail. To understand dipole-dipole bonding, let's have a think about a molecule. For example, hydrogen chloride. Now, we need to also remember one related concept, and that is the concept of electronegativity, right? And what is electronegativity again? Well, electronegativity is the tendency of an atom to pull in electrons toward itself. Now, if you're not too familiar with electronegativity, we do have a video on electronegativity that you can watch. But in short, chlorine is a very, very electronegative atom, much more so than hydrogen. So you can imagine that if you have the electrons sitting between them, chlorine is saying come here and hydrogen is saying oh come here, but its pull is very, very weak, well then the electrons, they're naturally going to want to come towards the chlorine. And so what's happened here? Well, we have unequal sharing. And the chlorine, it's pulled towards itself the electrons. And what happens when you get more electrons? Electrons have negative charge. So the chlorine is going to become partially negatively charged. What does this symbol mean? Well, that's the Greek lowercase letter delta, very similar to the uppercase version is a triangle. And the delta simply means partial, right? So we have a partial charge. So you can imagine it's less than one whole electron, because it didn't fully take away the electron. It might be like 0.3 electrons worth of charge. It's just a partial number. Similarly, this hydrogen here, it has a partially positive charge. Why is that? Well, it lost electrons, and when you lose negativity, then you become positive, right? It's like when you lose a very negative friend, you become more happy and positive. Okay, so here we can see that we have our hydrogen chloride with a negative side and a positive side. But so what? How does this explain the dipole-dipole bonding? Well, to give you a sense of why this is so, let's consider if we have a second one. Let's say this one is in red. And let's think about what's going to happen. We have let's consider what happens between this red hydrogen and this green chlorine. Well, here we have a positive charge and here we have a negative charge. Positive and negative want to combine, just like how north and south want to combine. So there is, because opposites attract, so there is going to be a bit of an attraction between these two atoms, right? The chlorine is negative. It says, hey, hydrogen, I think you're very beautiful because you're so positive, right? And vice versa. And this right here, well, what's this thing called? That is this force of attraction. This is our dipole-dipole force. Dipole-dipole bond, also called dipole-dipole force, whatever you want to call it. That is our dipole-dipole bond. And so that should hopefully give you a basic understanding of dipole-dipole forces. This is how it works. So it's fundamentally caused by a difference in the electronegativity. Now, let's go into a little bit more detail and explore why we call them dipoles. If we have a look at our HCl once more, we can see that we have a positive end and we have a negative end on the right. We call this a dipole. Why is that? Well, di means two and pole means like an axis, right? So just like how the Earth has a north and south pole, there is going to be an axis in which we can say that there is, a difference here. We can see that there's a positive end here and a negative end here. And so what we draw is we draw an arrow like this, and we put a plus, and we kind of put a plus sign on the end of this arrow to match with the positive charge there. So this is our dipole, and that's why we call it a dipole-dipole bond, because it's because of this polarity axis that allows us to kind of bond. The negative bonds with the positive. So now that we understand that, let's apply this with some example questions. Will this be able to undergo a dipole-dipole bond? What do you think? The answer is yes. This molecule will be able to undergo a dipole-dipole bond. Let's explore why. First of all, the first thing that we must do is we must consider the electronegativity differences between the different atoms. Chlorine is one of the top 4 most electronegative atoms that exist. So it's probably going to be able to suck electrons from our carbon. So if the electrons come over, well, what does that make chlorine? Well, it makes it partially negative, right? And if chlorine lost electrons, it's going to become, yes, partially positive. How about carbon and hydrogen? In reality, there actually is a bit of electronegativity difference between carbon and hydrogen. However, in contrast to the carbon-chlorine one, it's not really that big, so we tend to ignore it. We say that this bond here, the carbon-hydrogen bonds, are more or less non-polar, neutral. So what can we see here? Well, we can draw a dipole to represent this. And we can see that we have a net dipole, and that's fantastic. What does this mean? Well, if I have a second one here, well, what's going to happen? Well, I can see that even if I position it, we can see that between my blue chlorine, which has a partially negative charge, it's going to be attracted to my orange carbon because it's partially positive. So we're going to see that we're going to have a dipole force. Fantastic. Let's try another one. Will this molecule, carbon dioxide, be able to perform dipole-dipole bonding? The answer is no. And let's explore why. You might think so, because again, oxygen is extremely electronegative. So the carbon-oxygen bond should be extremely electronegative. So, and it is. So we actually do get a partially negative charge in the oxygen, and the carbon is indeed partially positive. Similarly here, this oxygen, it's also going to suck away electrons this way, and this guy's also sucking away electrons that way. So this carbon is actually like super extra positive, right? Now, so given that, why is this non-polar? Well, let's try and explain this. What's the problem is if we draw on the two dipoles that we have. We can see that because we have these two dipoles, they're going to cancel out. Just like if you add two vectors, if you walk 10 meters this way and 10 meters back that way, you haven't changed your position. We can see that our net dipole cancels out, and so there is no dipole. There is no dipole. So if there's no dipole, you can't perform dipole-dipole bonding. However, and this is extension, that's not to say that there's no interaction at all. If you did have a second carbon dioxide, there will still be attraction between this partially negative end and this partially positive end. But it's not called a dipole-dipole bond, even though it has very similar properties. It's just technical because it doesn't involve a dipole. Will this molecule, water, be capable of doing dipole-dipole bonding? The answer is yes. You might be tempted to say that, okay, look, this is pretty similar to the last one. The the oxygen is very electronegative. It's going to pull in the electrons from both sides. That means that this is going to be a partially negative on the middle. Because the hydrogen has lost electrons, it's going to be partially positive, and same thing here. But again, the problem is that if we were to draw these dipoles, they'll cancel out. This will be true. However, we need to think about the actual geometry of water. If you recall Vesper, water doesn't actually look like this. Water has a bent shape because of its two lone pairs that it has here, right? And what that means is that actually what our dipoles look like is that they'll be looking like this. And so if you were to add these two vectors up, well, what do you get? Well, if you would add these tip to tail, oops, you see that you do get a nice upwards vector like that. So the overall vector that you get is a big upwards vector like that. And so we do have a net dipole. Let's see if it works, right? So we have a partially negative here, partially positive, and so we're gonna grab this one, chuck it here. This hydrogen is positive and this oxygen is negative, so they're gonna love each other, and that's gonna be like a dipole bond. I hope you guys enjoyed. If you have any questions, please let me know. Other than that, I'll see you guys next time. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.